Sí. Hola, Cris.
Hola, ¿qué
Hola,
tal?
¿cómo estás? ¿Todo bien?
Sí, sí, hola Armando.
Hola, ¿qué tal? Estamos haciendo una prueba de sonido, luego tendré que editar el vídeo. ¿Qué tal, Cristina? Perdona, que es que estoy en paralelo con la emisión por YouTube y
Ah, vale. Sí, sí, tranquilo, que yo he estado en seminarios aquí en el... y sé cómo es.
entonces estoy ahí
¿Quieres
de...
probar a compartir pantalla?
Sí, uy, voy. Inhabilitó la función de compartir, dice.
Ah, sí, tenemos que hacerte coanfitriona, yo creo, para poder compartir. O si
Vale,
no,
sí,
espera un
porque me
segundo.
sale que lo tengo inhabilitado.
Convertir en coanfitrión también. Hala, ya eres coanfitriona, ya deberías poder ya.
Venga, sí. Vale.
Vale, en YouTube ya
Ahí.
funciona, ¿eh? Ya funciona en YouTube,
Ah, bien.
ya estáis ahí. Luego esto, cuando ya lo grabe, se quede grabado el vídeo, le corto la primera parte.
Ok. Y se ve, ¿no? Bien.
Sí, sí, perfecto.
¿Y el ratón se ve si me pongo aquí? ¿Lo estoy moviendo o no?
Yo no lo veo.
¿Y aquí?
Y ahí
Es
sí.
Ahora sí. Sí.
Es que tengo dos pantallas, vale, entonces lo muevo aquí. Va, mejor. Vale, pues ya está. ¿Lo dejo puesto
Sí.
o lo quito?
¿Cómo?
¿La dejo puesta o la quito? La presentación.
Quieras, como quieras.
Pues la dejo.
Yo lo que voy a hacer, como la vas a presentar tú, Enrica, ¿no? Yo me
Sí.
quito el vídeo para,
Vale.
bueno, para no aparecer. Venga, sigo aquí de todas formas.
Vale.
Mm.
Vamos a ver, ¿esto qué pasa? ¿Por qué no me... Ahora sí. Hola, Patricia.
Hola, Patricia.
Yo voy admitiendo desde aquí si quieres, Enrica, para que tú te puedas centrar en lo que
Vale.
es. ¿Vale?
Sí que llegan uno en uno.
Sí, yo estoy pendiente, no te preocupes. Y de la grabación
Vale.
también, de la transmisión también.
Hola, buenas tardes. Hola, Cristina.
Hola, buenas tardes.
Hola, Jesús, ¿qué tal?
Nada, me alegra mucho verte. Gracias por tu charla.
Un placer.
Voy a cerrar para no molestar.
Tú no molestas, ¿eh?
Enrica, ¿te parece que empecemos ahí? Hay 5. Yo estoy admitiendo
Sí,
aquí y
vale,
hacemos
esperamos un par de minutos más. Ok.
14 personas, pero vale. Yo sigo admitiendo incluso después de la hora, ¿vale? Después de que empiece el
Vale,
tiempo.
genial, gracias.
Nada.
Well, I think we can start. Good afternoon, everyone, and welcome to our IPARCOS seminar. Today, we have the pleasure to have with us Cristina Ramos Almeida from the Instituto Astrofísica de Canarias. Cristina was born in Santa Cruz de la Palma, Spain, and she studied physics at the University of La Laguna. She did her PhD at the ISC. In 2009, she moved to the United Kingdom for 2 years to work as a postdoctoral research associate at the University of Sheffield. She came back at the ISC in 2011 as a research fellow, and then she was awarded the Marie Curie Intra-European and Ramonica Hall Fellowships. Since December 2021, Cristina now staff scientist at ISC. She is the coordinator of the ISC research line Formation and Evolution of Galaxy and the principal investigator of the ISC research group Nuclear Activity in Galaxy. Today, Cristina will talk about multiphase AGN feedback on parts and kiloparsec scales. So thank you very much, Cristina. The floor is yours.
Thank you, Enrica, for the nice introduction. So hello, everyone. It's a pleasure to give this seminar. I would rather prefer being there with and see you in Madrid, but online has also its advantages. So I hope you can follow well the talk in this format. So today, as Enrica has said, I'm going to be talking about AGN feedback on parsec and kiloparsec scales from using a multi-phase approach. And so the work that I'm going to try to summarize here has been done in collaboration with the GATOS team, which I'm sure many of you have heard about, and also the QSOFEED team here at the ISC. Okay, let me start by mentioning something about active galaxies or active galactic nuclei, as we prefer to call them these days. Because, in fact, something that I always like to emphasize when I give these talks is that our vision of what an AGN or an active galaxy is has changed in the last years. And actually, one of the reasons why AGN have become so popular, it's because they are no longer understood as a particular type of galaxies, active galaxies, but instead they are considered as a phase, as a short phase indeed, that can be as short as 0.1 or 1 mega years. And this is very short in comparison with other galaxy processes, as it can be, for example, galaxy mergers that last for giga years. And actually, not only one, but several AGN episodes or phases can take place in galaxies, depending on whether there is gas to trigger the activity and feed the supermassive black holes. So considering that all galaxies, or at least all massive galaxies, have a supermassive black hole in the center, it might well be the case that every massive galaxy go through one or several AGN phases during their lives. So galaxies that we observe now as active might have been active in the past, and others that are not active these days, they have probably been active at some point, or will they become active at some point in their evolution. So this is so let me show this a snapshot from a simulation, a cosmological simulation, which is TNG50. This is a high resolution simulation in a small volume. And what we are seeing here is gas, actually gas velocity, with the black colors indicating low velocity and white colors indicating like the highest velocities. And what is happening here is precisely what I was saying before, that in this small volume, there are several galaxies containing supermassive black holes. And these supermassive black holes are accreting gas, as you can see, for example, here or here. They are accreting gas, and the reaction to this accretion of gas, it's feedback. Feedback is the effect that that this supermassive black hole has on the host galaxy. And here, what we are seeing is that the gas is ejected from this galaxy hosting supermassive black holes, and the gas is ejected at very high velocities and having an impact on how the galaxies evolve. So this is another reason why AGN became also very popular in these last times, is because these cosmological simulations predict and require AGN feedback for explaining many properties of galaxies. Actually, I think everything fails if AGN feedback is not taken into account in the simulations. One of the effects, the most obvious, at least from our interest, is this effect on the luminosity function that you can see here. No? So basically, if AGN feedback is not implemented in the simulation, the gas cools down very efficiently, galaxies keep forming stars, and they grow too big and start forming, as this one here. And this is something that we do not see in the real observations, which are the blue dots and squares in this plot. So the model requires feedback in order to reproduce the high luminosity end of the luminosity function. So today, I mean, because of this recent or not so recent anymore interest on active galactic nuclei from the point of view of the simulations, we observers started a massive search looking for confirmation of the impact of AGN feedback on galaxy evolution, and also to try and understand how things work in the central region of galaxies. And so today, I think we can say that we have plenty of observational evidence for AGN feedback or black hole feedback, name it as you want, on scales that go from the central parsecs of the galaxy, as we see here, for example, in this very nice ALMA works done by Santiago Garcia Burillo, to scales as large as hundreds of kiloparsecs. We see also the influence of supermassive black holes on in this case, on the star formation histories of satellite galaxies that are located at different position angles relative to the central galaxy, which is the one containing the supermassive black hole. So in this very nice work by Ignacio Martín Gamarro, they found that satellite galaxies located at certain angles from this central galaxy have different star formation histories than others that were located along the minor axis, and they found these in observations and in simulations. So The problem, so we find evidence for AGN feedback, as I said, but the problem is that when we compare samples of active galaxies with others of non-active galaxies, trying to see a difference between them in things that can track the impact of AGN feedback, as they might be star formation rates or global gas contents, we don't find such a difference, at least in the local universe. But this is expected because if we consider what I said before about the short time scales of the AGN activity, if we want to study the impact of the current phase of nuclear activity, which lasts, as I said, for a maximum time of 1 mega-year, perhaps, then the region we need to look at in order to see the impact of this AGN feedback is the central kiloparsec or so, the very central region of the galaxy. Because this is the same, this is the region having the same dynamical timescale as the AGN and the outflows that this current phase of nuclear activity drives. So this is what this talk is about. It's about looking at the central region of AGN of different luminosities using different gas tracers in order to understand how AGN feedback works and why in some galaxies this feedback is more efficient than in others. Then when we see effects on larger scales, like, for example, the M-sigma relation or these works led by Nacho Martín Navarro, we are seeing not the effect of the current phase of AGN activity, but the accumulated effect of these nuclear activity episodes through the whole of the accretion history of the galaxy. If we consider that the galaxy has been through different AGN phases, is the integrated output of these AGN phases rather than the instantaneous AGN activity, what causes galaxies to quench and what drives this scaling relation have, for example, the M-sigma. But as I said, this talk is about looking at the current phase of nuclear activity in order to understand how it's affecting the central region of active galaxies. And if we want to do that, so we can start from the innermost region where the action starts. And so we are looking at this tiny region in the center of galaxies. For example, here, there is a cartoonish view of how we think the center of a galaxy like this looks like. So we have the supermassive black hole, the accretion disk, and the corona. And surrounding this supermassive black hole, we have the gas clouds orbiting at very high velocities and beyond the sublimation radius where dust can exist because it's not too hot anymore. We have dust clouds in the Equatorian region, which is what we used to name the torus. And also we have dust and gas in the polar direction, so perpendicular to this torus, in the direction of the ionization cone. So back in 2017, Claudio Ricci and myself wrote this review for Nature Astronomy, in which we tried to put together the information that we had on nuclear oscuration in the central region of AGN, putting together what we knew from the infrared and from the X-rays. And something that we tried to transmit with this article was that the torus, this obscuring structure that produces the type 1, type 2 classification, that it's a little bit old-fashioned these days, I would say. It's not a static structure that simply does this unification model, but instead it's a very dynamic structure with complex kinematics, heterogeneous, and that varies, whose properties vary with the periods of nuclear activity. So it's something much more interesting than when we originally thought, and it's actually the connection between the ultimate connection between the host galaxy and the active nucleus. It's a material that it still belongs to the galaxy in a way, but whose central part is under the sphere of influence of the supermassive black hole. So it's a very interesting region to study because, like I said, the connection between where feedback is starting to develop and larger scales on the host galaxy. It's like 10 or even more than 10 years ago, when we wanted to study this nuclear region of AGN, the torus, and so on, we had two ways of doing that. Like very detailed studies could be done with using mid-infrared interferometry for nearby and bright AGN, as for example, Circinus or NG1068. And we have learned a lot from this first mid-infrared interferometry data of this nearby galaxy. But then if we wanted to infer properties of larger samples, what we did was to use data from large telescopes from the ground in the near infrared and mid-infrared to build these spectral energy distributions that we then tried to reproduce with the torus models that we had available at the time. And by doing that, we infer the properties of these nuclear regions, of this tori. But so at the beginning, originally, we were focusing on the infrared because it makes sense. It's where the dust re-emits the radiation that it's produced in the AGN. But then now we know that if we really want to understand what's going on in the central region of AGN and of galaxies in general, we need to adopt a more multi-wavelength perspective. So now we do not only use the infrared observations, but also we take advantage of the X-rays and also of the sub-millimeter regime, thanks to ALMA. ALMA has represented a revolution in the study of the torus because it has permitted to study the molecular gas and also the coldest dust within the torus. And it allows us to study the kinematics in this tiny region in the center of the galaxy using these CO transitions or HCN, like the different transitions that we can study in the sub-millimeter range. And like putting together all this multi-wavelength information that we have of the central region of AGN, we have come up with this scheme that is the most accepted one these days that Sebastian Hennig put forward in 2019, where he tries to connect all the information that we gathered from the near infrared, the mid infrared, and also the sub-millimeter. So, for example, if we look at the near infrared using very high angular resolution, for example, using gravity, we study the innermost part of this torus, the dust that is very close to the sublimation radius, and we see these rings, very small, of 0.2 parsecs. So we are really talking about tiny things here. Then, if you have seen this very recent work by Violeta Gámez Rosa, in which they use data from Matisse, which is mid-infrared interferometry, but now they are able to obtain images because they have a much better coverage of the UV plane. So they have found evidence in the mid-infrared for dust in the equatorial direction, but also in the polar direction. So this is basically what we are seeing here. And this polar emission that I was mentioning has to be a hollow cone. It has to be empty in the inside, because otherwise we would never get to see the central engine of the AGN, and we would never see, for example, the broad lines that are produced in these BLR clouds that are orbiting the supermassive black hole at very high velocities. So it has to have this hollow cone shape. And in the case of ALMA, we can study using CO. We can trace the bulk of the mass of the molecular gas mass, and we found that this mass is concentrated in the equatorial plane, the more classical torus, if you like. And this is what we see mainly when we observed with ALMA. So putting together all this information, as I have said, we have come up with this scheme that so far reproduces the observations that we have recently acquired with all these instruments. So now I'm going to talk a little bit about the work that we are doing within this GATOS collaboration. GATOS stands for Galactic Activity, Torus, and Outflow Survey. It's an international collaboration of more than 60 people now, led by Almudena Alonso Herrero. So it's a Spanish-led international collaboration. And so we are trying to study how the nuclear region of this AGN are and how the feedback starts in AGN of low to intermediate luminosity. So Schiffer-like AGN. So we are in this first paper led by Almudena. We studied a volume limited sample of 12 Schiefferts selected in the X-rays. Half of the sample show this polar emission in the mid-infrared, and in the other half we do not detect it from the using ground-based telescopes. And so now something that has also changed in the thanks to the new observations that we have, but also to the models, because the models have evolved also in the last years, trying to reproduce all these observations that I was mentioning before. And now we can not only look at whether we detect polar dust or not, whether we detect torus versus polar dust, etc., but we can also try to understand if this polar dust or emission that we are seeing in the mid-infrared, it's just dust sitting in the narrow light region, or whether it's part of this AGN feedback cycle that is starting in the nuclear region of AGN. No? So in this diagram from Almudena's paper, what we are seeing showing is the prediction from this semi-analytical model by Marta Venanzi, in which they studied like different conditions in AGN that are more or less favorable for launching polar infrared outflows. So this is, they explore the effect of the infrared radiation pressure on dusty gas, and they see which conditions are necessary for launching these polar outflows. And so what we find here is that there are certain conditions. In particular, we need high Eddington ratios or high AGN volumetric luminosities and moderate column densities in order to have the conditions to launch these polar outflows. So here we are representing so this is the model, and these are the observations from Almudena's paper with the different symbols indicating whether we detect the polar emission or not, or equatorial, or just unresolved emission, like in this source here. And what we find is that some of the galaxies are indeed very close to the predictions of the models, for which we would expect to detect these infrared polar outflows. And in the case of other galaxies, like for example this one, that it's far from this prediction from the model, it can be that the dust that we are seeing in the polar direction is just dust that is sitting in the narrow line region. So now, like I said, we are trying to investigating whether what we are observing is part of the AGN feedback cycle, or it's something that it's more static. And something that we find also from this work, and you can see in this plot, is that the polar component is more relevant for the more luminous AGN, whereas the torus or the unresolved mid-infrared emission are more prevalent at low volumetric luminosities. This can be because of this, what these model predictions tell us, but it can be also a problem of sensitivity, because these are ground-based mid-infrared observations, and when you are at low luminosity, it's not so easy to detect this mid-infrared emission from the ground. So this is where the James Webb it's going to make a big contribution, because targeting these low luminosity objects to see how is the nuclear material distributed in them will be very, very important, and will help us to put a lot of constraints to these models. Actually, so this is work done by Almudena, like very detailed for these objects, but a more statistical sample was studied by Omaira González Martín, and in these two papers that she published in 2019, she did this SED fitting with torus models that I was mentioning before, that we can do for inferring the properties of larger samples and see how, and look for trends, no, in AGNs of different types, luminosity, etc. So she took a big sample of AGN, observed with IRS Spitzer. She did the composition using different templates to isolate the AGN contribution and fitted them with all the models that are available in the literature, like torus models. And what she found is that precisely this, that at higher volumetric luminosity, the SEDs require the inclusion of this polar emission, so torus plus wind, whereas at lower AGN luminosities, a torus component is enough. So this might be telling us again that as the AGN become more luminous and the Eddington ratios are higher, we are more, galaxies are capable of launching these nuclear polar outflows that we see in some of the galaxies. And because of this, we need the inclusion of these components in the model to reproduce them. So like I said, we need the James Webb for several reasons, especially to study this low luminosity AGN, but not only. And in cycle one, our GATOS collaboration was awarded two proposals, one led by David Rosario to observe a subset of the GATOS galaxy with MIRI in the mid-infrared using imaging. So there are galaxies with known polar emission in order to characterize these polar extensions using different MIRI filters and get to know the temperatures, the SEDs, etc. And then we also got another proposal led by Taro Simishu, in which we are going to use MIRI MRS in order to characterize the multiphase outflows in this galaxy in the very central region. And we want to see if this polar emission is co-spatial with the disturbed outflow kinematics that we are expecting to see with MIRI MRS. We haven't got any MRS data yet from our program, but we got some of the imaging. And actually here, what I'm showing are like the first images that they were taken in July, I think, of one of the GATOS galaxy, NGC 5728. So this is the HST image that you can see that there is a very nice star formation ring here. And this is the MIRI image in this color combine of these three filters before PSF deconvolution and after the convolving from the PSF. And so, as expected, we detected the polar component in this galaxy. And we are, like I said, trying to characterize this. David Rosario is leading this work. But something that I would like to emphasize here is the quality of this mid-infrared imaging. Because if we compare it with what we used to have from the ground in the mid-infrared, I mean, this is a whole new world, because this is how this galaxy look like in different mid-infrared images taken with the VLT. I think they're all from VLT, and also some of them from Gemini with T-Rex. And you can see that basically we are limited to detecting the nucleus, and that's it. And in the case of MIRI, we see this, but we also see this beautiful star-forming ring. So it's like, I mean, day and night for mid-infrared astronomers. So it's stay tuned for the results on the GATOS MIRI imaging. And also, I would like to mention the exposure time. No, like this imaging only took like something like 5 or 10 minutes to be done, whereas this we are talking about perhaps an integration of 1 hour or even more than that. So this is also part of this is not part of these two programs that I have mentioned from the James Webb, but I would like to publicize this work that has been published using data from the early release science programs, and also warranted time and all the public data we have from James Webb so far. So in this case, for example, Miguel Pereira Santaella studied the Cipher galaxy in the Stephan's quintet, NGC 7319, with MIRI, to study the interaction between the low power jet that this galaxy has and the interstellar medium using different gas tracers. And what we've found, what Miguel found in this paper, is that the interaction of the jet that this galaxy has, that it's you can see here in contours, it's interacting with the galaxy ISM, and when the jet shocks the region where we detect dust lanes in the infrared, we find enhanced molecular gas and also ionized emission in this region, probably produced by this interaction between the jet and the ISM that is accelerating the jet and producing this. And also another result that it's based on the on this public data of AGN studied with the MRS also by Ismael Garcia Bernete. In this case, we studied the pH emission, the emission from the polycyclic aromatic hydrocarbons, which are normally used as star formation tracers in galaxies, including AGN. And so Ismael looked at the mid-infrared data of 3 galaxies, 3 AGN from these programs. And he also compared the pH features that he detected in the nuclear region and also in the star formation regions of this galaxy, and compared them to theoretical pH models that they have of these pH features. What we found is that whereas the nuclear pH emission, it mainly comes from neutral pHs, which are larger and more resilient. In the star formation regions, for example, in this galaxy NGC 7469, which has a beautiful star-forming ring around the nucleus, the pHs are dominated by ionized grains, which are smaller and less likely to survive the harsh AGN radiation. So he concluded that the AGN has a significant impact on the ionization state and also on the size of the pH grains on scales as small as 150 or 250 parsecs. So please have a look at these 2 very nice papers if you are interested. And as I said at the beginning, ALMA has been a revolution in the study of the torus and in general of the nuclear region of AGN, because it allows us to study the kinematics of the molecular gas. And this is what we have done, for example, in the case of the galaxy NGC 1068, one of the most nearby and well-studied AGN. And so something that we found is that, as you can see here, this is a torus of NGC 1068 that ALMA resolved for the first time using data from cycle 2, if I remember correctly. As we have gathered more data from the following ALMA cycles, we have seen that the torus, as I said at the beginning, is not an isolated structure, but it's connected through molecular gas streamers with other parts of the galaxy, in this case with the circumnuclear disk of the galaxy, NGC 1068. So this is a ring of molecular gas that has this very nice ring shape, devoid of gas in the center. But you can see that the torus here is linked to this CND through these molecular gas streamers that are consistent with the outflowing gas that it's leaving the torus and impacting on the inner surface of this ring. Santiago Garcia Burillo has led this GATOS study of some of the GATOS targets, so Cipher-like luminosity, and also did the similar thing for the NUGA galaxy, which are lower luminosity AGN, and he produced this very nice plot after looking at the spatial distribution of the molecular gas in this galaxy. And what we are showing here is the concentration of the molecular gas in the central region of the galaxy. So basically, this ratio here tell us how concentrated the molecular gas is in the 50 inner parsecs of the galaxy, so torus scales, as compared to the central 200 parsecs, which is more like the scales of this ring of molecular gas, no, the CNG. So what we found is that in the lower luminosity AGN, in the Nuga galaxy, the molecular gas is more piled up in the center. And in the case of the GATOS, as we go to higher volumetric luminosities, the concentration of molecular gas it's the opposite. It has been shifted from the center to the outskirts of this region, so it's more spread out. And we believe that it is due to the action of AGN feedback that is pushing the molecular gas outwards. Because of the impact of the AGN winds and the jets that are happening in this galaxy, and producing this kind of morphology similar to what we are seeing in NGC 1068. And actually, the galaxies that we see here in this part of the diagram are the ones showing clear evidence of molecular outflows. So this is an indication that indeed AGN feedback is producing this correlation, let's say, this trend that we see in this plot, and pushing the molecular gas outwards. So now, to finish with this seminar, I would like to tell you something about what we are doing on higher luminosity AGN. So now I have been talking about low to intermediate luminosity AGN, but now I would say a few words about high luminosity AGN, in which we also see the impact of AGN feedback in the central region of the quasars in this case. In some galaxies, like for example NGC 2110, we have seen this effect of the AGN feedback devoiding the central region of the galaxy of molecular gas, in this case induced by a jet. But also in the quasars, so luminosity of 10 to the 46 or so, we see that the impact of feedback is having an effect on the distribution of the molecular gas in the central regions of these quasars. So let me introduce you a little bit this sample. It's we call it QSOFEED. And it comprises like all the most nearby and most luminous quasars in the Reyes sample, which is an optical selected sample of AGN without broad lines. So we make sure that they are obscured AGN, no? So we don't have a direct view of the central engine of the AGN. So this leaves us with a sample of 48 quasars, type 2 quasars, which are high luminosity AGN. So we have they are more likely to show outflows, so AGN feedback in action. They are nearby, so we can resolve the outflows, and also because they are type 2 and we don't have this vision of the central region, we can study the continuum and model the stellar population, which is a key part of this project. And also they have a wide range of radio power and galaxy morphology, so we can study the influence of these properties on the outflows. So this is the whole of the AGN team at the ISC at the moment, and this is the part of the team who are working on this QSOFEED project. We are collecting like a lot of multi-wavelength observations in order to study the outflows and also the impact of these outflows on the host galaxies, mainly but not only with the GTC and other telescopes here in the Canary Islands. And the basic goal of the project is to study, characterize this outflow, these winds launched by the supermassive black hole using different gas tracers, ionized, warm molecular, cold molecular, and this is part of the PhD work of Giovanna Speranza here at the IC. And then we want to study the impact of these outflow properties on galaxy properties that happen on this central region that we were mentioning before. So they are happening on the same time scales as the period of nuclear activity and the outflows. And we want to look at these properties using data from the James Webb. We will apply for time to get observations in cycle 2, so we can target these pH features that are good tracers of star formation. We are doing also a stellar population modeling using optical data, and also we are studying the molecular gas on small scales using ALMA. So let me say a couple of words about this very nice work on the modeling of the stellar populations that by Patricia Bessier here at the IEC. She's a postdoctoral researcher working in the team. So she took, in the case of one of the quasars, she took a keck cube that covers the whole of the optical range from the 3,800 angstroms to almost 6,000. So it's a good wavelength coverage to model the stellar populations. And so she found a young stellar population in addition to an intermediate and an old stellar population. But here in this plot, I'm showing the percentage of young stellar population younger than 100 mega years, which is what we want to compare with the outflow properties. And this galaxy has an excellent laboratory to look at the interplay between the outflow and star formation, because it's almost phase on. And also the outflow that we trace with the oxygen-3 emission, it's developing in the plane of the disk. So we see the approaching side of the outflow and also the receding side. So this is what I'm showing here in blue and red. So this is the ionized outflow. And what we find is in the approaching side of the outflow, there is an increase in the percentage of young stellar populations, and we don't see the same on the other side of the galaxy where we see the receding side of the outflow. So what we believe is happening is that as the outflow pushes and shocks the interstellar medium, at the front of this outflow, we see this increase of the young stellar populations, and on the opposite side, because the turbulence is higher and also the energy that the outflow is injecting is higher, it is too much for promoting star formation. So it's like the outflow is introducing the right amount of turbulence in this region here, but it's too much in this other part here. So we don't see the same effect happening. So we believe that it's a very nice example of positive and negative or preventative feedback happening on the same galaxy and induced by the same outflow. And it shows, I think it's beautiful because it shows the complexity of the problem, because if you have all these integrated in a single fiber, like for example, if you study it with the CSS, then you have everything mixed up and you don't get to see this detail of what is going on in this galaxy. No? So we need especially resolved studies like this one in order to understand how what's going on and how the feedback is affecting different parts of the galaxy. We got some time with the GTC Megara to observe a subset of our sample and trying to do this same analysis that Patricia did with the Keck cube. And so hopefully we will get the data anytime soon. And as I'm running out of time, I just want to briefly tell you about our ALMA observations of some of the quasars. So we targeted a small sample of 7 quasars of the quasar feed sample in CO221, sorry, with ALMA at 0.2 arcsecond resolution, with that the distance of the quasars correspond to 370 parsecs. And we tried to select a sample that covered was representative of the whole of the sample in terms of morphologies, radio powers, etc. So we have interacting galaxies, mergers, spirals, and also red early type galaxies. And so we went and observed them with ALMA using this CO line. The first result is that we didn't detect the red early type galaxies, these 2 guys here, in CO. So AGN having the same properties, they have the same oxygen-3 volumetrics, oxygen-3 luminosities, the same stellar masses. They are very different in terms of molecular gas contents. So my quasars are the circles here. So these are the red ETGs, and these are the spirals and the interacting or merging galaxies in blue. So you can see that we are talking about completely different beasts in terms of molecular gas mass. So this implies that not all quasars are in gas-rich galaxies. There are some that are almost depleted of CO, or at least they have very low CO compared to the other ones. So it's galaxy morphology which might be driving the difference in molecular gas in this galaxy. And we compared also with the main sequence galaxy from Cold Gas and Atlas 3D to look at the depletion times. And for the quasar, we found depletion times due to star formation only between 100 and 500 mega years, whereas for main sequence galaxies, it's more like 1 giga-year. And the ULIRCs, which are not represented here, would have like depletion times of 10, 30 mega years. So our quasars are somehow in between in terms of molecular gas content between the ULIRCs and the main sequence galaxies. But with ALMA, we have the resolution to study the galaxy morphology in CO and also the kinematics, which was the most interesting thing for us when we put forward this proposal. So you can see here the detected quasars in CO221, the interacting systems, and here the spirals. So you can see that the morphology are very different. Some of them, they look very disturbed, something that has no comparison with the optical images because they do not show these double-peaked profiles that we see here. And so a difference that we found between the interacting systems and the spirals is the concentration of molecular gas. We find that the central kiloparsec contains more gas in the case of the interacting systems than in the case of the spirals. So this is a first difference between the two. But like I said, we were more interested in the kinematics, and we were expecting, because these quasars have like high volumetric luminosity, we were expecting massive molecular outflows, like the ones that are detected in some ULIRCs, like, for example, this famous work by Claudia Ciccone, in which they see high velocity wings. But instead, as you can see here, we found very boring CO profiles, so nothing spectacular. Not very high velocity wings, like a lot of turbulence, but not high velocity wings. So we had to really dig in to get to see if they were molecular outflows. And we found evidence for molecular outflows in the end by doing, by fitting and rotating these models, studying the residuals, looking at the inclination of the galaxy. So really hard work to interpret the molecular gas kinematics. But we found evidence for these molecular outflows in the quasars, and we found that these outflows represent only between 0.2 and 0.7 of the total molecular gas mass in the galaxies. Very moderate outflow velocity, maximum of 350 kilometers per second, compact radii from 0.4 to 1.3 kiloparsecs. And the outflow mass rates are also quite low, between 8 and 16 solar masses per year. So again, in terms of outflow properties, we also find that the quasars show intermediate properties between the molecular outflows of Seyfert galaxy and the ones of the ULIRCs. And if we plot, so this is the very well known in the AGN community empirical relation between the outflow mass rate and the volumetric luminosity of the AGN from Fiore and collaborators. And so the blue dashed line is the fit to the data that Fiore compiled in his paper. And so the idea is that the more luminous the AGN, the more massive the molecular outflows that they drive. So originally, we were expecting our quasars to be somewhere here in this relation, but instead they are sitting here in this part of the diagram. So either we pick the most boring quasars in the sample, which is a possibility, or as we start to look at more AGN and get larger and better samples, we start populating this part of the diagram. And actually, we know now that this is the case because there is a recent work in which they studied the Puma ULIRCs, which are like a larger sample of ULIRCs, no? Which are also, they have the expected high molecular outflows. And they found that they also, there is a very large dispersion in this part of the diagram here. This is a very nice work by Isabella Lamperti that you can also look using ALMA and the same transition. So our interpretation of this result is that the outflow mass rate does not depend only on the volumetric luminosity, but other factors as the power of the jets, how it's the coupling between the winds and the jets, whether the jets and the winds are happening on the plane of the molecular gas disk or not. This has an influence of how much, how massive the outflow that you drive are, and also the amount and the geometry of the dense gas in the central galaxy. So there are other factors that we need to take into account in order to see when feedback is more efficient or more important in galaxies. No? So this is a little bit, this is to give you an idea of our interpretation. No? Like if we have a jet or a wind that it's developing on the plane, it will drag more massive molecular outflow. And if it's something more like has an angle relative to the CO disk, then the molecular outflow that you are able to launch will be less massive. So I think I ran out of time, so I'll leave this with the conclusions, and thank you very much for listening.
Thank you very much, Cristina. Great talk, very interesting results.
Thank you. A bit long, sorry about that.
So now we have time for questions. Let's see now, YouTube channel. Well, if not, I have a couple of questions. At the beginning, you show that several torus models have been used to derive the torus parameter, the Nenkova, the Fritz model, and Honig.
Yeah.
And I was wondering, did this method, did they get similar results when constraining the effective, the radius of the torus, of the covering factor, or the dust on mass?
It depends. I mean, actually, there is a very nice paper by Ismael Garcia Bernete on the comparison between the different torus models applied to a sample of Seyferts that has been just accepted. And it's very tricky to compare this because, like, for example, the covering factor of the different models are not the same. Like, for example, the Nenkova model, no, they have like
depends on the geometry.
It depends on the geometry, and also it depends on how many models the modelers produce, because there are some of them, they sample very well the parameter space, but others not so much. So, for example, the Hennig models, I think the range of covering factor was much smaller than the Nenkova. So it's difficult to make a comparison between them. We tried in this paper, no, and you can do something, but they are so different, no, especially once you incorporate the wind, that it's very difficult to compare parameters. Yeah. Right. So it's more like a matter, it became more like a matter of whether you need the inclusion of this polar component or not, yes, than comparing like the detailed parameters.
Yes, and concerning to the mid-infrared polar dust, what kind of composition do you expect to find in the polar direction?
This is very interesting because this is one of the things that we were expecting to do with the James Webb. Because one of the predictions from the models is that if this polar dust is polar outflow, in principle you should expect to detect graphites, because graphites are bigger than silicates. No, the composition that we normally work with is silicates and graphites. And so if we find a large percentage of graphites in the wind, it would imply that it's a wind, because it means that they have been dragged from the very central region outwards. And if we don't find any, it's more likely to be the other possibility, that it's just dust in the narrow line region. So yeah, so this is one of the things to look at.
Well, no other questions? Well, before you mentioned that with the ALMA data, you are now able to characterize the kinematics of the torus. And do you know if there are any results using an inflow instead of an outflow in AGN?
If there are results of a particular AGN, we see
can affect the properties of the torus.
Well, so the ones that we have, the thing is that detecting an inflow is always much harder than detecting an outflow, because inflows, I mean, when you see, for example, higher velocities, you can ascribe them as outflow, no? Whereas in the case of the inflow, gas doesn't go like directly from here to the center, no, like the outflow, but it has to go in smaller and smaller orbits, no, and so it's difficult. It's more difficult to detect inflows than outflows. But I mean, as far as I can remember, on the torus scales, we haven't seen evidence for inflow. Also because it's easier, like I said, easier to track the outflows. But it would be possible, because normally we look at these position velocity diagrams, and knowing the orientation and everything, is possible to see whether what you are seeing is inflow or outflow. But on these small scales, if I remember correctly, we haven't seen evidence for inflows from the ALMA data.
Okay, thank you.
But there has to be inflow, because there has to be gas going to the center.
So, okay, if there are no more questions, thank you very much, Cristina, again, for the great talk.
Thank you.
And thank you, everybody, for joining us. So, bye.
Bye.
Hello.